Okay, thank you very much. Okay, it's a pleasure to give a talk here. The pity I'm not there. Okay, and the purpose of my talk will be twofold. I mean, I'll have first some introduction on effective field theories and how this is useful for phenomenology. And I'll have a second part, more theoretical, where I will try to push in the direction that the effective field theory should be considered from the on-shell perspective, okay, that I'll try to convince you that it's much easier. And not only that, that you get a lot of information that is usually missed when you do effective field theories with fields and calculation a la Feynman, okay? So let me proceed, okay? Everybody I think knows what is effective field theory. This is based in the idea that we assume that the standard model is a good description up to some large scale, lambda, that we don't know where it is now, okay, where probably we'll have new state, new physics, okay, but at least we have a mass gap between the standard model scale around 100 GeV and this scale lambda, okay. Of course, this is not an assumption that we are putting out of the blue, okay. It's an assumption based on many tests of the standard model that we have not seen particles around these scales. Of course, but of course, nature could conspire, and it still is possible to have light states. This is not a theorem, but there is many examples telling you that these particles, if they are there, should be heavier than the standard model ones. Okay. Taking this assumption, okay, this is an assumption. Now you can simply Taylor expand, okay, the standard model fields and derivatives over this lambda. Okay, so even that you don't know the general Lagrangian, you through this expansion, you at least can parameterize your theory, considering only the light states that are the standard model states, okay? And now in the expansion, the leading term, of course, are what you do an expansion in operators or in terms with fields, and is a expansion that counts the number of dimension of the operators, okay? The leading order will be dimension 4, subleading dimension 6, I'm assuming here Lepton and baryon number, okay, for simplicity, okay, you can include them also. So the first leading term will be the standard model, of course, that we know. And now if we're interested in beyond the standard model, you have to go to the subleading terms, okay, leading in beyond the standard model that are dimension 6 operators. Now we know all dimension 4 operators are the standard model is in the textbook. When you go to this dimension 6 operator, you find that there is a lot of them, okay? It looks like, I don't know, you can count them, 100, depends how you count it, 100,000, okay? But you get the feeling that probably there is little to say here, okay? Because it looks like everything is allowed, and it's difficult to understand the implications from these operators in a generic viewpoint, okay? Of course, you can just look at this few examples, okay? And now you have little, I mean, some concrete physics, and you'll have less operators, but in a general perspective, looks like everything is allowed. But that's not true, okay? Not everything is allowed here. And the key point probably I want to say here is that there is many correlation between observables already at the tree level. Why this happens is because even there are accidental symmetries, okay? So in these dimension 6 operators, still there are some symmetries you didn't impose, but they are there, okay? For example, you find that there is deviation on the Z and the W couplings to fermions are related, okay? If you have deviation on the Z coupling to fermion, there should be also deviation from the W to fermions. And the reason for that is an accidental custodial symmetry that appear in these dimension 6 operators, okay? So again, this is not a symmetry you ask for, this is a symmetry that you have accidentally there in dimension 6. So what it means is after we'll measure so well the Z measurement at the lab, okay? Now we don't expect, so we got bounds of per mil, we don't expect big deviation of the W to fermions at the LHC. They will not reach this per mil level, okay? And in fact, if you look at the data, it looks like it's in perfect agreement with the standard model, okay? So in some sense, knowing about lab, now we can say something about what could be at the LHC, okay? What could be the deviation? This deviation cannot be large to be seen at the LHC. Also, this custodial symmetry plays a role in to realize that the Higgs to ZZ, or Higgs to WW, well, the W is virtual going to fermions, are related, okay? If you do the ratio between 1 and 2 is something the experimentals measure, but now this is not an independent deviation, it's related with other ones. In particular, you can write this equation okay, that relates the deviation that you can have in this ratio of the Higgs to Z to W's as a function of deviation that you should have in triple gauge coupling or Higgs Z going to Z gamma, okay? So the fact we have not seen deviation in these three observables means that we cannot expect deviation here, okay? In fact, we have, now you have a relation between deviation. So if we measure very well triple gauge coupling, as it is the case, and we have very strong bounds on Higgs to Z gamma, it means that we don't expect to see this at the LHC, okay? So other experiments are more important than this one, and this is due to the fact that you have relation between these dimension 6 operators. Now, there is another part of more important, that is the correlation that appears from operator mixing, okay? So even if you think that all these terms are generated at some high energy scale where you have new physics, of course, you have to run down, as we have seen previous speakers, to the electroweak scale, or even lower if you're doing B physics or I don't know, whatever, lower energy physics. And now because of this, there is a mixing between these operators. So when you look at an observable, this is affected by many different operators, okay? And this is now you find correlations that are useful, okay? So this is why effective field theories are useful. You can relate observables, okay? Let me put a couple of examples, okay? For example, if you're looking for CP violation in the Higgs operator, something like H squared FF tilde, okay? And you are doing this at the LHC, now you can see that this term can generate the loop level electric dipole moment, okay? You have to plug this operator Higgs to gamma gamma into a fermion, and now you have a contribution to electric dipole moment that we know have a strong experimental bound. Okay, from that we can derive that this has a bound on this coefficient in front of this operator. For example, it has to be much smaller than 10 to the minus 5. Okay, so you see that even that this operator, we can try to measure at the LHC, there is little hope that we will see it, okay, because they have already strong bound coming from another experiment that is electric dipole moment. Okay, similarly with lepton flavored violations, okay. For example, we can have a violation of the electron number, okay. For example, these two operators, one in concrete, this one could give you Z going to mu E, that we have been searching at the different experiments, or this one that will give you, when the Higgs get vacuum expectation value, give you Higgs going to mu E, that is also searched at the LHC. Okay, now again, effective field theory tells you that if you have these two operators, they can mix into the dipole operator mu going to E gamma, okay? And now we know that we measure this observable very well, okay? And in fact, in the future, we'll measure much better. Okay, so we see that bounds coming from mu to E gamma, telling us that there is no hope to see this deviation of flavor, this flavor violating decays at the LHC, okay? It's interesting here to remark, because it's bringing me to the second part, okay, that this operator mixing into the mu E gamma appear at the two loop level. So you could say, okay, why there is no one loop? And this is the point I want to make now is stress now. Later, in fact, it's because you can draw a loop there, but it cancels. Okay, surprisingly, when you calculate it, you give you to 0, to the logarithmic running of this operator into the mu E gamma. Okay, so in fact, this cancellation is not something found in one example. It's found in many examples, and it has been unexplained for years, because nobody understood why there is no symmetry there. And you do the loop in the usual way, and you see only at the end of the calculation that they are 0. Okay. In fact, let me put some examples, because I will we'll talk about them. For example, I mean, I pointed out one. Okay, it was pointed out before this one. Okay, this operator at the one loop level can bring a dipole operator. Okay. The diagram is there, okay? It's only when you calculate the logarithmic contribution is 0, and also the 4 fermion operator. For example, this is very relevant for flavor physics when you do a loop and there is no contribution to the dipole operator at the log level, okay? At the running, doesn't give you running to this coefficient of this Wilson coefficient of this operator. There are other examples in Higgs physics, for example. If you look at this operator for Higgs to derivative operator, you can close the loop and generate something like 2 Higgs to two photons on operator like this. So a priori, you have the contribution. The loop level is only when you add all together, you give 0 the leading order. There are also more interesting examples that not only when you look at the logarithmic contribution, also if you look for finite terms, okay? For example, we were reporting this paper, and it was known, of course, before that you look for a finite term from G-2 from a particular BSM, okay? In this case, not all of BSM, but a particular BSM like where you have a heavy singlet plus a doublet fermion. You do a loop, again, the loop is there, okay? But when you calculate, you see that the leading contribution 1 over m squared, okay, where I'm assuming m is the mass of the heavy particles, the heavy singlet and the heavy doublet fermion, okay, they cancel, okay? There's a cancellation against Myrick-Poll's cancellation, and you only get a subleading term 1 over to the m to the 4. That, of course, is much smaller if m is larger than the scales at which you do the measurements. And also you can find this finite term cancel in Higgs gamma gamma. For example, if you have a replica of leptons with the standard model quantum numbers, okay, so heavy E plus L fermion, you see that they don't give contribution to Higgs gamma gamma at order 1 over m squared, and only get contribution 1 over m to the 4. Okay, so this kind of cancellation, this kind of many zeros that you find into effective field theory is asking for a better understanding. And this understanding has come out in the recent years using effective theories, but not from fields, but from amplitudes, using on-shell amplitudes. Okay, so still we can call it effective theories, okay, but not fields, okay, anymore. Okay, you start with defining your amplitudes on shell, okay, and consider, of course, amplitude is closer to the experiment. So for experimentalists, it's much better than an operator that contains fields, okay, from which you have to derive the Feynman rules and do all the process. Here you start from amplitudes from the beginning, okay, and define your theory from amplitudes, not from a Lagrangian. Now, it's an important gain in simplicity, okay? Remember, when we do fields, in the fields, we have ghosts, gallstones, p squared is different than 0, okay? This brings all the complication with gauge invariance, okay? However, when we go on-shell amplitude, we only have physical states, okay? For example, for photon will have 2 helicity plus and minus, the same for the gluon, the same for the graviton. Okay, and that's much, and we don't have ghosts, neither ghostones, okay? So this is the gain of simplicity, okay? And here is an example, okay? But you can proceed everywhere in the standard model and in the dimension 6 operator. Okay, let's go for the dipole operator, ENew, sigma Higgs. Okay, this is the dipole operator. Now, what it means an amplitude, I don't talk about fields anymore. I talk about an amplitude, two fermions, a Higgs, and a W. Okay, automatically you realize that there's only one way to write it, with helicity minus for this guy. If these are minus, everything should be minus here. Okay, so it's not a possibility to have minus plus, or plus minus. Okay, so it should be all minus. Okay. And that's interesting information that you are missing when you look at here. Looks like all helicities are allowed. And in fact, you can write this operator, this amplitude now, on-shell amplitude, using the spin helicity formalism. I don't want to describe here, probably you are not familiar with, but if you're familiar with, or you want to be familiar with it, it's very simple, extremely simple to derive the standard model and all the amplitudes using this formalism. I put it at the end of some slides of how to do it. But I encourage you to learn it, okay? This is just a formalism, very simple. Instead of writing p squared as a p mu, as a 4 vector in the Lorentz group, you write it as a product of spinors, okay? I don't want to talk here because I don't have time, okay? But so the idea is, okay, know any more about fields, you start always everything with amplitudes from the beginning, okay? Now, of course, as I was interested in loops, the first thing you could ask me is, oh, how are you going to do loops? Because of course, 3-level amplitude is nice, but when you do loops, we know it from the Feynman approach, okay, that we have diagrams like this one, and all these particles have to be off shell, okay? You put them on shell, you're going to get it wrong, okay? So those particles have to be off shell, okay? Now, how are you going to do it? Okay, this has been asked long ago, of course. I mean, this on-shell amplitude business has been running for years. And people realize that, of course, if you look for the imaginary part, okay, of this diagram, okay, that correspond to cutting here, we call it cutting, and means putting on shell these two particles, okay. Now, this looks like more a product of two on shell amplitude, okay, because you put these particles on shell. Okay, now this is an amplitude, on shell amplitude, and now this is another on shell amplitude. And in this way, now you can get what the loops are following this approach. Now, still there is some connection to do. For example, you have to connect the imaginary part to the anomalous dimension, but there is a clear and easy way to do it. Okay, so the imaginary part, in fact, gives you the anomalous dimension, the running of the Wilson coefficients. Okay, and now you can write a final formula that looks like here. You can get the exact expression. I didn't put here the pi's and the details here, but they tell you that the anomalous dimension can be written as a product of two amplitudes, one here on the left, another one on the right, integrated over the phase space. This is not the loop integration. This is a phase space integration. So in some sense, the anomalous dimension related with these three particles scattering to this one, and now this to one rescattering again to these three ones. Okay. And you can do it for all the anomalous dimensions at the one loop level. Okay. And now you can see a lot of information. Let me go a little bit faster. An emergent selection rule that you didn't see when you were doing the loops a la Feynman. Okay. For example, as we were saying, there is no contribution from four fermion operators like this one, okay, into dipole. Okay. You can do the calculation, see that give you 0, but now we can understand in our way, calculate the anomalous dimension to the dipole as a product of two amplitudes. Okay, here is the cat, you have this amplitude here and the other amplitude here. Okay, I have to just calculate this three-level amplitude and integrate over the phase space. But I don't have to do it to see a 0. Okay, I can see that this amplitude is 0. Okay, in the standard model, this amplitude doesn't exist. Why doesn't it exist? Because it's well known for years that when you look, again, this is the good thing when you go on shell amplitudes, because you're talking about defined fields, states with defined helicities. Okay, so in the standard model for a theory, or in general theory for gauge boson and fermions, also for graviton, if you look for a amplitude which has all minus helicity, this is 0. So this amplitude is absent in the standard model. Okay, it's a total helicity minus a half for the fermions, minus 1 here for the vector. Okay, so you need to have this thing. Okay, this amplitude here, there is no the other one. So you see automatically this amplitude is absent, and this now you understand why these loops were 0. Okay, and now you can proceed in different ways. Okay, now you have this selection rule that tells you, for example, also why this operator was not inducing a Higgs operator with FF. Okay, again, I can look at this in the formula where I have two amplitudes. And again, I have an amplitude with minus here. Higgs going to two photons with minus helicity. Again, this is absent in the standard model. This is the reason why this diagram, you don't have to calculate anymore. You know this amplitude is 0, now is 0, okay? This approach gives you a lot of information, okay? Also beyond the zeros, okay? The on-shell approach. It also tells you relation between anomalous dimensions you never expected, okay? Let me tell you here an example. A beautiful example to me, okay, is the renormalization of psi bar psi operator. Now you have it to the dipole, and the operator F square H square to the dipole. Okay, these are two contributions from two different operators to dipole of a lepton, okay, or of a fermion. Now they look like completely different. Okay, so they look like a loop of fermion here, completely different. You don't expect to be a relation. And in fact, if you want to calculate, you start the calculation with one. After that, you do the calculation for the other. I don't think you can use anything with this calculation. Now, how it looks like from on-shell approaches, again, your anomalous dimension is a product of two amplitude integrated over the phase space. And now you start seeing relations, because this amplitude is exactly the same amplitude as this one. For two fermion going to a vector and a Higgs, two fermion going to a vector and a Higgs. Okay, so you realize that the anomalous dimension of the two are related, are coming from the same standard model amplitude. Okay, so these two ones will give you the similar things. And you see that when you calculate one, I mean, there is a recycling process here. On shell, always everything that you calculate is useful. Keep it, because you will use it later. For example, if you calculate this anomalous dimension, you needed this amplitude, you can, of course, use it later on. Okay. But there is also more information. For example, if I look at the dipole on shell, on the amplitude, okay, not as a operator, as on shell, I can see that this EL are in J equal 1, angular momentum, okay, only in J equal 1, okay, so this J equal 1, lepton to lepton going to Higgs W also in J equal 1. And now I know that when I calculate loops, the amplitude should be also J equal 1, okay. So in some sense, what I need for this amplitude I was saying to you before, that I need to calculate the dipole, the anomalous dimension, so the one loop running, is not the full amplitude, is only the partial wave j equal 1. Okay, so it only depends on this number. Both anomalous dimension depend on this number, is a number. Okay. And of course, you realize also that if you put here another amplitude that has not j equal 1, another j, okay, there is will not give you contribution. Okay, so there is an angular momentum selection rule that you could not see again from the doing the approach à la Feynman. Okay, and this allows you to understand also a lot of zeros. Okay, apart from the one I was talking related with angular momentum selection rules. Okay, so I'm saying in many cases, not always, you can write something like the anomalous dimension is a product of partial wave numbers. Okay, not always, but I mean this. But many cases in the standard model dimension 6 operators, or the corresponding amplitudes to this dimension 6. Okay. Now, is it possible to go beyond one loop? Of course, it is possible with the same ideas. People have been doing this for QCD in many examples. For us, that we are interested in BSM in acting at some scale down to the experiment, it is useful to me. There's a way to go. Okay, and it's extremely simple, even at two loop when there are no one loop process. Let's say you calculate, as we said, some cases you calculate one loop and this is 0, but because of this selection rule I was mentioned, and now you want to calculate the leading term that is two loop. Okay, now in this case, this contribution are 0, and what is remaining is extremely simple. Again, it's a product of two amplitudes where you integrate over some phase space. For example, the example I was telling you before, okay, how this operator enters into mu e gamma. Okay, this operator, okay, is when you hit the vacuum expectation value is what gives you a contribution to z to mu e, to the observable z to mu e. How affect this? Well, as I said, at the one loop level, it is 0. You have to go to two loop. Okay, and here is the diagram. Okay, but you do it on shell. Again, you can look for the imaginary part. Okay, this related, the anomalous dimension can be related with this imaginary part, and now you see that this two loop is a very simple thing. You have just to calculate this amplitude, multiply by this, and integrate over the phase space of these three particles. Again, it's something like two particles scattered into 3-1 that rescatter again to these ones. Okay, so it's a three-level on-shell process. Okay, and in this way, the way we calculated this interesting fit back from mu z to mu gamma, sorry, z to mu e relation with mu to e gamma.
Excuse me, you have
Yes.
3 minutes.
Sorry?
You have 3 minutes.
Very good. Okay. So briefly, in the last 3 minutes, finite terms. Okay, as I was mentioning before, it was the anomalous dimension, what is called the logarithmic running, how I enter one to the other, but it also finite terms I was telling you there are zeros. Okay, and also on shell you can do it, and we were doing this for understanding the loop, the cancellation I was telling you before. That if you take a model, there's like a heavy singlet and a doublet, and you calculate the contribution to -2, you see that the leading term 1/m² is 0. You don't understand why, but only appears at the some leading term. Okay, now if we do it on shell, we realize also can be related with this imaginary part by cutting this diagram, so putting these two particles on shell. But you can do it in two different ways, cutting the L or cutting the S, that give you the same contribution because it's, as you can see from the diagram, is even under exchange of S and L. Okay, it's the same here in S and L. I cut an L here, I cut an S, but the diagram is exactly the same. Nevertheless, if you look now simply to the amplitude here, this is a three-level amplitude. There is a propagator of this guy. It's 1/p² minus ms². P² is on shell because this is an amplitude on shell, and the on shell is the mass of the p² is the mass of the L². So you get something like 1/ml from this propagator, 1/ml² minus ms². That is odd under exchange of S and L. Okay. Okay. In some sense, you go here, you have the opposite sign. Okay, for this propagator. So you can see that you have from the two diagrams something you expect to be even under SL, but now the propagator appear here is odd under SL, and this is the reason. Okay, this is a symmetry reason to understand that this gives you a cancellation. Okay, and this is thanks to the fact that we can cut. This diagram is very simple. These are three-level propagator, and I can see if it's odd or even under the exchange of S of L. And now with this technique, you can go and find another lot of zeros. Well, not a lot, but few more. Okay, for example, you have scalars, heavy doublet, and charged fermions. Again, you can do the same. You have a diagram, and you see that you have is even under exchange of N and L, but the propagator is odd. Okay, so again, give you 0. And now you can go also to Higgs gamma gamma, as I was saying before, to understand that this gives you zeros. Okay, so the on-shell perspective give you an argument, a symmetry argument. There is this parity here that to understand the zeros that were found and explicitly from Feynman calculations. Okay, so let me conclude. It is obvious we have to consider standard models and effective field theory. Okay, so these higher dimension operators are, of course, there waiting to be discovered. Of course, we don't know the scale at which they appear, at least in Planck scale for sure. But it's useful to understand, has been useful to understand the correlation that you derive from that, because relate experiment and tell you what experiment is the most competitive, okay, can do the better job to constrain new physics, okay. Now, the second part, I was more to push to the completely different perspective, effective field theory, not about fields, but just on amplitudes, okay. All particles are on shell. The simplicity is enormous to me, okay. So you don't use Lagrangian anymore, much better related to experimental physics. Calculations are simple because at the level and easy to recycle. You do a calculation, you can use it to the other one, okay? And what we see from that is many emergent selection rules that tell you when contributions are 0 or when contributions are related one to the other, okay? As we have seen by several examples. Okay, thank you very much.
Thank you for the very nice talk. So now, questions. Yeah, Jim.
Or should I stop?
Can you hear the question?
No, I cannot hear anything.
No, it was off. So sorry. Can you hear me now?
Yes.
Okay. Hi, Alex. So the question is the following. In the finite term that the magic 0 in the finite contribution to the G-2 that you mentioned, there was a paper by Craig pointing out that there is a symmetry for which is that the same symmetry you're talking about?
It's kind of related, yes. It's kind of related. Not exactly the same. Yeah, but they kind of related because at the end they talk about a parity. Okay.
But then I see a difference. I mean, it's of course it's extremely interesting what you were saying, but it seems that the magic 0 in the anomalous dimension, the divergent parts, they are you find a more of an operational reason of identifying them. So it's not the reason. You find the operational method to identify them, but not the reason. While in the case of a symmetry, you can claim it to the symmetry of the reason. So is there some fundamental difference between the finite and the anomalous dimension in that respect or not?
Well, the anomalous dimension still there is some symmetries. For example, for example, the helicity conservation, okay, or angular momentum conservation, okay, that tells you they are 0. It is true that you could say at the end relies on the fact that there are some amplitudes that are 0 in the standard model. Okay, so you relate the fact that you have a 0 with some other zeros, and a deep understanding why those amplitudes are called highly maximal helicity violating amplitudes are 0. You can prove it, but why it is there, it's probably, and I cannot tell you into seconds. Okay, so it's something you can prove, and it happened also for QCDs or for gravity. This is well-known fact. Also, probably people didn't look too much into the standard model, but still there is helicity conservation there that tells you that okay, everything can be related to these amplitudes that are 0. Okay. And also angular momentum to me is more clear that you have angular momentum conservation tells you some operators also don't enter. So it is true that probably is slightly in the other cases, it's more related probably with a parity that you have there. But still in the first case, there is also symmetries plays important role. So the selection rule I was talking I think also plays important role. Yeah, I don't know why in one case is, I mean, I don't know if there is a, of course, it's much easier the first part, the second part of finite terms, more complicated. But I mean, a priori, more complicated a priori, but at the end of the day, it turns out to be quite simple for these examples. I don't know if you go to other examples, how it looks like.
Yeah, we can have one more short question.
Yes.
Hi, Alex, this is Gautam Bhattacharya. So the example that you gave on the example that the amplitude is 0 when there is an odd term in the propagator 1 over ml square minus ms square. Right?
Yes.
These kinds of arguments are valid for specific type of models. I mean, you know, I mean, how general this is, I mean, it is not clear. So if you take a particular example, maybe it works very well. I don't know about its general applicability. I mean,
yes, indeed. I mean, this shows you that there is little, I mean, some examples, but no, I mean, if you take other example where you don't have, as I was saying, the two cuts, I mean, there was one loop and now you can cut it in two ways. That tells you that there is two contribution from the two cuts that are even under the interchange. This is not generically true. Okay, so absolutely the zeros in the finite pieces are not something, I mean, I don't know if you have done calculation, they usually think you don't get zeros, okay? But there were few examples, and in fact, we looked more, we found some other examples that I don't know, were in the literature, we put them in the paper, but I didn't know they were there in the literature before, inspired by this idea, okay? So now you know that if you have this symmetry, this kind of symmetry, when you cut the diagrams, you will have a zero, okay? But there are not many of them. And I don't know if I was inspired, we were inspired by this calculation of the G-2 from the singlet and the doublet. I mean, I don't know if I can use it beyond that, okay? If I can use these techniques to show more zeros, okay? Right now, we found more zeros, but using the, as you said, when there is a simplicity in the models, okay? So it's a small class of models where you have this parity there, yes, indeed.
I think this is related to what John also asked. So it seems to me that the main point of the analysis is to realize that the anomalous dimension is related to product of some on-cell amplitudes, right? So the main fact is that some of the on-cell amplitudes are zero, and which in any way, you know, we know, and then the additional fact is just unitarity, right? So
no, also the selection rule of the angular momentum, okay? Because you start with something has some helicities, okay? So these two diagrams, the helicity should be conserved, okay? So there is also helicity conservation important there. So it's helicity conservation apart from unitarity and all these things, okay? But the important thing is still helicity conservation is still there. Now, why now? So this allows you to relate this thing to an amplitude with a defined helicities. And now if you're asking why this amplitude is zero, it happened to be zero in the standard model. Okay, but that's true. That is probably the part that you have to say, okay, this is zero, we know it happens, and you can prove it. Okay, there is a easy way to prove this thing. But it's not a symmetry. I don't know. It's a mystery kind of. Okay, why all these type of amplitudes are zero? Okay, but it's something well known.
No, but I'm saying that is the main question. The next step, once you understand that, the next step is just relating imaginary part to a product of amplitude. So on-cell amplitude. So
yeah, this interesting part why these amplitudes where all the helicities are plus or all helicities are minus. Well, I have to say there's an example with the Higgs that is not true. Okay, so it's not a theorem. Okay, because there is an example where this thing is not true. When you interchange a Higgs, you can have all helicities minus, and this is non-zero in the standard model, but it's only coming from the Higgs. So you know that there is only one source of this amplitude. It's not the one I was putting there.
But
cannot appear.
naively isn't just Lorentz invariance, because that's the only thing you are using in this on-cell method.
No, minus is possible. There is no problem with Lorentz invariance. All the helicity minus is possible. The amplitude transform under the Lorentz group, under the little group that are helicities is not invariant. You get a phase, so it's not invariant. Okay.
No,
so,
and plus the little group transformation properties.
Plus the little
and,
group,
and
exactly.
dimensional analysis, of course.
Exactly. So there is the little group transformation there. So it's not a symmetry. So all the helicities are possible there. The only thing is helicity is concerned. That's the only thing. But that's a mystery. I don't know what to say. I mean, there has been known for years that these are zero. I mean, the first time you calculate graviton, and you realize that if you put all the graviton, it's a long contribution. People realize all gravitons have equal helicity. This is zero. Okay, that's happened for graviton gauge bosons. As I said, it's not a theorem because we have a theory where a Higgs that doesn't happen. Okay, so it's not something deep root in some principle, some symmetry behind. But it's a very generic rule that has been known, and yeah, but I cannot say more there. Okay, I can prove it to you. It can be proved easily that this way happens. Okay, and I can give you argument why this thing happened, but it's not something like a symmetry argument.
Okay, thank you, Alex, and let us thank all the speakers of this session.